Introduction to Probabilities, our tutorial. This week, Jeff and Allison introduced a new part of statistics, probabilities. Jeff discussed some discrete and continuous random variables, like the binomial and uniform, and you saw their mass and density functions in a graphical form. Allison then talked about sampling distributions and what happens in the long run. R has a few functions we can take advantage of when trying to calculate probabilities from a known distribution, or plot the mass or density functions. Let's start by looking at a discrete binomial distribution. Recall in the lecture on probability distributions, you worked through an example where a fair coin was flipped 3 times, and you let x equal to the total number of heads observed. We know the distribution of x is binomial, with 3 trials, and the probability of success, or heads in our case, equal to a half. Of course, we know that x can only take on values from 0 to 3, and they must be integer values, since it is a discrete distribution. To calculate the probability at any particular value of x, we can use the function dBinom, which stands for distribution binomial. For example, the probability that we observe no heads, so x is equal to 0, is 0.125, or 1 over 8. To obtain the whole distribution of this binomial random variable, we need every possible value of x and their probabilities. So let x equal to a sequence of numbers from 0 to 3, increasing by 1 with the sequence command. And let prob x equal to the probability of x from this binomial 3.5 distribution. We'll combine the results for better viewing, and now we can see the whole distribution with all values of x and their respective probabilities. We can plot x and the probabilities with the plot command to get a better idea of what this distribution looks like. Notice that we specified type is equal to h to obtain bars similar to a bar plot. And we can calculate the mean as well by just taking the sum of all x values times their probabilities. And as you might have guessed from the graph of the distribution, the mean is equal to 1.5. Similarly, we can do this for a binomial random variable with sample size 50 and probability of success 0.2, just to get an idea of what the binomial distributions can look like. For an example on continuous distributions, we can look at the uniform and normal. For the uniform 0-1 distribution, let's start with a sequence of numbers from -1 to 2, a sequence of length 100 to have a lot of points available. Then with the dunif command, which stands for distribution uniform, we can obtain the distribution function at each x value and plot these to see that the uniform 0-1 takes on the value 1 whenever x is between 0 and 1, and 0 everywhere else. Similarly, for the standard normal distribution, we create a sequence of values for x from -3 to 3 and obtain the distribution function with the dnorm command, which stands for distribution normal. And lastly, in the sampling distribution lecture, Allison discussed samples and their properties after repeated trials. We will recreate the sample of the binomial 10-0.5 distribution that you saw in the lecture with the simulation coin tossing. If we wanted just one sample from this distribution, we can use the rbinom function, which stands for random binomial. We can specify that we would like just one sample from a binomial distribution with sample size or trials equal to 10 and the probability of success 0.5. We can see that in this one sample, we obtained 4 heads. Let's try creating 1,000 samples. That is, we would like to perform 1,000 experiments where each consists of tossing a coin 10 times. We'll store the number of successes or heads for each of the 1,000 experiments in binom sample. With the table command, we can see what our outcomes were and how often we observed 0 successes, or 1 or 2, or so on. We can save these frequencies and plot them to get a visual representation of the samples obtained. Don't be surprised if the numbers you obtain are very different when you try to do this yourself. After all, these are random samples, and just like in real life, when you toss a coin, you know that the outcomes you get in one sample can be very different than in another sample. But what should remain the same, even if your samples are different, are the properties of the sampling distributions you learned.